It's 6:30 sharp.
So is it ready?
Yes. Should we start?
Okay.
I think we would start this session and let them come. Means the people are joining, or already some people already joined over here, and some of them will be joining later also. Okay, but I think that we will definitely start at 6:30, and it is 6:30 sharp right now, so
6:30.
we should.
So would you
Okay.
start? Would you start with the introduction or?
Yes, you start it.
Yes.
Okay. And Sayan, you can give some introduction
Okay.
to them. Means what exactly we are going to listen. Actually. Okay, you start.
Okay. So, good evening, everyone. Today we are going to talk about some applications of complex networks in modern computing. The speaker is from Somyajit Chakraborty, and I just like to thank Professor Avijit to moderate us, and also I'd like to thank all of the participants who joined with us in this program. Complex. So I just request to Somajit to you can start with your presentation, and we are going to. Somajit?
Yeah. Okay. So thank you, Shanda. I'm Somyajit Chakraborty. Good evening, everyone from Techno University, West Bengal. So today we are going to understand the applications of a very important topic. Quite simple, though the name suggests is complex, but it's quite simple. So complex networks in modern computing. How complex network affects modern computing. So that's our topic. So today we will take a journey through our day-to-day lives, and we will find some very effective applications of complex network in our life. Relatively, another thing I have to say that the complex network is a very important topic, but the problem is many people are very much confused about what complex network actually is, and it is relatively unknown to many undergraduate students who I think it is very important the topic, and everyone should know about this topic because the applications of this topic is huge. Okay, so without delay, I think we should start with the presentation. Okay, so first, we have to define what a complex network is. So this is very simple. A complex network is basically a graph. It's kind of connection between various entities in a web-like manner. So why it is complex? Because the number of entities, since the number of entities are more, it's quite random in nature. Since it is random, so that's why it is termed as a complex network. Yeah, so that's the definition of a complex network. Now let's start with the components of a complex network system. So what are the basic components that any rough complex network system should contain? The first component are the nodes or the elements about which we are going to study, or on which two certain topics or certain important objects about which we are going to study. So that is the first component, which are sometimes known as called as the vertices or nodes. So that is the first component. The next are the links. How these nodes, how these objects which we are going to study are related. So that are known as the edges or links. And the second, what kind of network is it? So graph and network, they are two separate terms, but mathematically speaking, roughly speaking, they are both the same, but there is a slight difference. Now network is a graph, but it is a vast graph. Now it's a semi-infinite graph. It's not completely infinite. It might be infinite, might not be infinite, but that is a network when multiple graphs are connected. So that we can call as a network. Another is a basic graph. Okay, so these are the three components we need to define any rough complex network system. Okay. Now, yeah, a rough difference between a network and a graph. A graph is basically related to something very specific, a specific topic. A graph of a, for example, in a Facebook, you have friends. So that network, the network of friends, you can actually term it more as a graph. It's not because there are so many users in Facebook, but only with certain users you are friends. So that is known as a social graph. So graph is a smaller unit of a network, that we can say. But in general, mathematically speaking, both are the same thing. So the main mathematical elements, the naming is different. For network, we call it node. The objects of interest are known as node, and the connection between them are known as links. And for graphs, they are known as vertices, or a single vertex, and edges or edge. Okay, so these are the main elements main elements of difference between graphs and networks and how they are related. Yeah, so very important thing, a perspective of so studying networks. Why should we study network and how the study has to be done? It's a very important thing. Now, why should we study network? First of all, studying network is very important because most of the objects in the universe, even in our day-to-day life, we are connected. We are a social animal, so we are connected with each other. So that connection we need to in order to understand that connection, we need to perform certain analysis. Now that analysis can only be done with the help of networks, because that is what define us. These are the defining blocks of our economies, defining blocks of our social structure, defining block of our entire cosmos in general. Now, how do we study them? That's a very important question. Now, how do we study such networks? First, we can study the individual components. For example, the nodes. We can study only the nature of nodes. Then we can study the connections or the interconnections, the links between each nodes. Those are known as we have discussed earlier, edges. So by nature, so we can study the nature of individual components, nature of connections and interactions. And thirdly, a very important observation that we can do is study the patterns, how the nodes are connected, the patterns of the connection between nodes. Now, that is a very important job because that will provide us a rough architecture, a structural view of the network. Now, what kind of network it is. Next, we can study the behavior of certain elements. See, if we change certain elements, certain parameters of a network, we will see the behavior of the network changes. Now, that is a very important observation. So in that way, it can help us to abstract out the system, help us to summarize the system based on certain key parameters and how it can affect the growth or growth or destruction. There's certain whether it is an evolutionary or it is a static system. So we can understand such nature. We can abstract out such nature of abstract out the nature of the graph or a network by studying those behaviors. Yeah, so these are the main methods by which we can study any kind of network. So yeah, there are roughly two kinds of graphs, as we all know. If you are acquainted with the graph theory, then you should know that there are two kinds of graph, roughly speaking, undirected and directed graphs. Now, directed graphs are also called as digraphs. So these digraphs generally represent two entities which are coherently, means they are related in such a manner that one entity affects the parameters or growth or staticness of another node. So that is a directed graph. For example, URL of URL. For example, any web page. For example, when you click a link in a web page, it transfers to another web page. Yeah, so that link, it is directed to certain another link. So that is links between different web pages. So that is an example of a directed directed graph entities. Then we have phone call records. Now when we call someone, we call from one direction to another. It's like that. So it cannot be like we can call from both sides, calling from both end. That is not a concept. So we can call from one side, from either side. So phone calls are directed networks. And metabolic reactions, there are certain metabolic reactions which are causal, which are caused due to one effect and then second effect. So it's a stepwise, it's a cascade process. So those are also directed networks. Now undirected networks, most networks are undirected. As you can see, there are protein interactions are there. For example, any networks of roads, some networks of roads are undirected, some are directed, some are undirected, mostly undirected, because there are vast networks of nodes, and many nodes basically produce cycles. So that is, in one way you can come back through another way. So in that way it's an undirected graph. Many social network relationship, that is also undirected in nature in general. So that is the main difference between undirected and directed networks. So what are the main aspects of complex networks? What are the key aspects? What are the models available for starting complex networks? So the first is the Erdős-Rényi model. We will describe it in much more details in the next slides. Then we have the collaboration networks. We can study collaboration networks with the help of complex network models. We can also produce ego networks or social connections, how the behavior of the social connection changes. That is known as an ego network. Then we can have trust networks, basically whether you should trust an entity or not. That is in order to understand whether you can trust a particular entity. For example, doctors, for example, lawyers. So based on that, we can produce trust networks about them. Then we can have game theoretic models. Now, those of who you are acquainted with the economics, so you will be quite familiar with the term game theory. So it's a balancing theory between agents. So game theoretic models can also be sometimes modeled with the help of complex network. Next, there is the Barabasi-Albert model, which we will discuss in extensive details. Then we can also, in the recent onset of COVID-19, we can also basically monitor the outbreak of COVID-19 through complex network. Then we can also understand the risk assessment in supply chain disruptions, general supply demand networks, say economic networks mostly. So these are the all main parameters with which we can basically, with the help of which, through which the complex network models can be implemented to understand the key aspects of these theories. There are other factors also, other models, other aspects which can be studied with the help of complex networks, which we will also discuss. Okay, the first use of a complex network was in 1980s and 1990s. It was during the depression, during the American Depression. There's a huge downfall of there was a huge economic downfall. So there was an urgency to create network of companies who have been affected the most, or who are the cause behind such downfalls. Economic entities were caused behind such downfalls. So Mark Lombardi he was the first person to apply complex network theory to produce a network system to monitor financial fiascos, means financial fraud detection. They basically created a financial fraud detection system by applying complex network. That was the first application. Okay. Yeah. Tim Berners-Lee basically invented www. That was basically modeled after the Barabasi-Albert model network. Firstly, it was made with the help of Erdős Rényi. Then it was gradually changed to Barabasi-Albert. But the modeling of www started with Stanford University in 1990s. So that was a very important. That was where one of the very important applications of complex network. And it's a huge one, and from that day, it's probably still now it is not. It is completely used to understand the nature and how the internet is growing. Since it's an evolutionary model, more and more users are coming into the internet. So it's an evolutionary model. So it is studied. The nature of the internet, the web of internet is studied with the help of complex network. Okay, it's a rough animation which we're going to see. Yeah, so the data, the availability of data is a lot. The huge availability of data. Now, how can we correlate those data? How can we connect those data? Now, that is our main goal. Now, if we want to connect those data, we need complex network theory to correlate between various social entities so that we can basically formulate a generalized theory on how these social entities behave, how the social entity act by itself and also as an entity completely. So this animation shows us how the data is in rising gradually, and we can monitor each and every aspects of those data. Okay, so rough. So here is an animation of rumors. See, in recent events, we have also seen that in recent events of COVID-19 that there are a lot of rumors being spread about the disease, about the causality of this disease. So that rumors, the flow of rumors, can also be studied with the help of complex network theory. Okay. So our most important part of any complex network theory is real world analysis. Since most of the mathematics was first that basically modeled complex network theory in the early 80s, more like early 70s and 60s, they were not based on real world application. They were much more theoretical, they were much more crude. So we needed a concept to understand how real world complex networks behave. So scientists, mathematicians came up with a theory known as random graphs. So the theory was actually there, but they applied it to complex network theory. So random graphs are very important while studying complex network theory. So how random graphs behave? See, any normal graph behaves in a pattern. See, we can observe a pattern, but in random graphs there might not be pattern. For example, a certain relationship could be generated just at random. We might not know how it came into being, but we just know that that relationship exists. So that started. So those kind of relationship can be explained with the help of random graphs. Okay. So how should edges be placed? So the placement of random edges in case of random graphs, see, all graphs have edges. So the placement of those edges, now how these links are produced, how any kind of connection is produced is through stochastic means, that is through probability distribution. Actually, the degree is nothing. If you are familiar with the term probability mass function or probability density function, then you will be able to understand that the probability distribution, the degree of any graph, a particular node. Let us assume that there is a particular node of any graph. So that node, where that node is connected with another node. Now, how the edges are linked, that can be done. That can be done. Say, let us assume this is a node, and there is another node here. So, and this is connected in some way. So, wait for a second. Yeah. So this is a node. This is another node, and these two nodes are connected. Now, how these two nodes are connected, that should depend upon the probability distribution of this probability mass distribution of the degree of this node. That means how this node is connected with other nodes. So that will affect the relation between these two nodes. Yeah, so that is how the probability distribution works in this scenario, in this particular case. So there are three main models while studying random graphs, as we have discussed earlier. Erdős-Rényi model, which is an exponential perspective. Then we have the Watts-Strogatz model, which is also called as the small world method or small world approach. Then we have the very revolutionary concept, the scale-free model, which is the Barabasi-Albert model, also known as the power law distribution model. So, yeah. So let's start with the Erdős-Rényi model. So I think we all know the name of this person, Paul Erdős. He was a famous number theorist, and Alfred Rényi was another great mathematician. So yeah, so their theory was very simple. They believed in a combinatoric model. So what they did actually was, if we assume that there are n number of nodes in a particular network, then the connection between nodes should be NC2, means it should be the maximum possible edges that can be formed between these n number of nodes is NC2. And the formation of node is given by a probability function P, which is again depends upon the degree distribution. Okay, so here's a simulation. It's a rough simulation of the Erdős-Rényi model, a graph. You can see the graph, the edges are being produced at random. So that's how real world complex network works. We cannot just simply create a link between them without knowing for sure how that happens. So it's in random. So this network, as you can see from this equation here, I'm not going into the mathematics in detail, but in general, this is basically binomial in nature, as you can see. So binomial in nature. So since it's a binomial degree distribution, it's not, in general, it's not a very realistic function. Now, why it's not realistic? Because in case of real world problems, in case of when we talk about real world networks, it is seen that binomial distributions are the least functions which pop up. Mostly they are exponential, but they are not in general binomial. It can be logarithmic, but they cannot be binomial. So a basic combinatorial relationship, that will not be enough to explain whether a link between two nodes should be produced or not. So that's a very important point that we should understand. Now, what is a very important limitation of this model. Okay, so yeah, so application. So Erdős-Rényi model, when it came out in I think it came out in 1984 or 85. Yeah, so the model came into being in 85, but the application came much more later, in 2000 after the 9/11 attack. So the most important major aspect was there was so many list of people who were confused, who responsible for the 9/11 attack in the world of the World Trade Center in 2000s. Yeah, so the 9/11 attack, the people who were responsible, they were basically put into random network, random graph and random network, and they were being narrowed out. That's a process in network theory known as triangulation. It's a very common practice in maps which also use network theory actually. So triangulation, so they triangulated uh, the most important, the key members or the key handlers of those attacks. So the terrorist network application was the first biggest application of Erdős Rényi model. Then we have the applications of ego networks, formation of social networks between social connections. So that's a very important aspect, also very important application of Erdős Rényi model. Okay, so small world model. So as we have seen, the Erdős Rényi model has some limitations, some big limitations. See, binomial distributions are not realistic in nature. They are not realistic functions. So Watts-Strogatz came up with a better model known as the small world approach. So they believed in clustering. Now, they believe that individual networks, instead of going and studying the entire or the network in its entirety, why don't we study the network where there is high clusters or huge clusters of connection, it's huge clusters of edges. So networks with huge edges are calculated first, and then the light edges. Then the density of edges where the density is low, where the edge density is low, then they are studied. So that's a very important method. So that actually changed the degree distribution into exponential one instead of a binomial distribution. But still, some traces of binomial distribution it remain. So we will see later that Watts-Strogatz model is also not a very reliable model in case of real world application. Okay, so this is a rough simulation of Watts-Strogatz model. So as you can see, the graphs, the connection are formed at a random, but where there is high degree of edges, only there the network edges are being formed. So that's a huge point here to notice. So that method is known as the clustering. Now the clustering is done with the help of a clustering coefficient. The coefficient is calculated with the help of the nodes where the connection is more, where there is more number of edges, the nodes with more number of edges, so highest degree. So that is how clustering coefficient is calculated for Watts-Strogatz model. Okay, so here is the probability function or the degree function of Watts-Strogatz model. Yeah, it's big. I know it's a quite big mathematical equation, but you don't have to be afraid. Basically this probability function, if we generalize it, we will see that it is nothing but the Dirac's delta function. If you are familiar with it, it's quite used in quantum mechanics actually. So Dirac's delta function. So in one way it is exponential, in another way it's binomial, but the right term of such expression is basically Poisson expression. I'm writing the spelling. So it's a French mathematician, named after French mathematician. Poisson expression. It's a Poisson expression. So this kind of this is also a good model. This is very close model actually to a real world method, to a real world problem. But yet, due to its binomial nature, it still suffers from the same problems which we have seen in the Erdős Rényi model. Yeah. Okay, so let's so advent of the scale-free networks. Now, scale-free, most of the real-world problems we will see that they do not have certain scales. They do not follow a pattern. Now, scales are not really present in real-world situation. So for that, they follow a certain power distribution, some exponential distribution. That is also known as a power law distribution. So this is a very famous power law. So the degree is proportional to a particular constant, which is again a power of another constant. So that is basically a scale-free network. So random graph. Okay. Now, another theory, a very important theory that mathematicians of complex network theory came to realize is the Matthew effect. Now, the Matthew effect is biblical. It was there from the first Bible was published. So it is very, I think you can relate with it very much because it's a very common idea that life is unfair, right? Life is unfair means the people with more money will get more, and people with less money will obviously get less. So that's a very important position, important idea. So it's Matthew chapter 20. It's first quoted in Matthew chapter 25 verse 29. So Matthew says that for to all those who have, more will be given, and they will have an abundance. But from those who have nothing, even what they have will be taken away. So that is known as the Matthew effect. So scientific in scientific sense, for example, if we have to understand this effect, for example, we know two scientists. Okay, a famous example is Marconi and Sir Jagadish Chandra Bose. So Sir Jagadish Chandra, it is argued that Sir Jagadish Chandra Bose was the first person to invent radio. Yet Marconi at that time was quite famous. He was quite famous to the Westerners. So he also, maybe simultaneously, he also invented the radio at the same time. But he got more more recognition than Sir Jagadish Chandra Bose. Same thing happened with Tesla, Nikola Tesla, and what's his name? Oh, whatever. Okay, so yeah. So that is the Matthew effect. So people with more recognition. No, that's not Faraday. Okay, so people with more recognition will obviously be recognized more, and people with less recognition will they will not get recognition as much as the people with more recognition. So that's how Matthew effect works. That how life works actually. So that gave us the idea of a new concept known as Alfred Edison. Yeah, right, Shanda, right. So Alfred Edison and Nikola Tesla. So both of them were kind of big in the electronics market. But Nikola Tesla was much more into scientific world instead of application, whereas Edison was much more in the application side. So Edison got much more recognition than Nikola Tesla. Yeah, sorry for that. Okay, so preferential attachment. So Matthew effect gave rise to the very important theory known as preferential attachment. According to preferential attachment, you will see that the nodes, it's only applicable to evolutionary models. So in evolutionary models, even in static models also. So new nodes, when we add new nodes to a certain network, the new nodes will be added to only to those nodes who have highest degree of connections, right? The nodes with highest degree of connections will attract the next node or the new node coming in. So let me explain it much more better way, pictorially. So this is a node, and this is a new node, and there is another node here. So this node has a lot of connections, as we can see, and this is the new node. This is the new node, and this is another old node, but this has only two connections. This has four connections, as this is two connections. So this new node will obviously get attached to this node, not this node. So that is how preferential attachment works. Okay, so the idea behind preferential attachment was first developed in 1920, first applied in 1925. So it was by Yule, who studied the genetic classification. So he basically studied the species number, so number of genus in flowering plants. So Yule in 1925 he first applied preferential attachment. Then it was studied by Simon in 1955, who worked on the citation network. But probably the biggest of the scientists who actually worked on citation network was Jonathan Price in 1976. So in 1976, the first idea behind a groundwork of citation network was laid in 1976. And then we have obviously Barabasi and Albert. So Barabasi-Albert model invented, actually practically revolutionized the World Wide Web with the help of preferential attachment, which is applied in nowadays in also in even in now you can witness this network preferential attachment, this behavior. You will see Google uses a page ranking algorithm, right? So the page ranking algorithm works on this principle, preferential attachment. With more number of hits, pages with more number of hits will be connected with another page which has much more higher uh, degree of hits. So that is how the Google crawler accounts the pages in Google database. So that is preferential attachment. So this is a rough history of preferential attachment, which is currently there. Started with Polya, Gregory Polya, then started with Yule, which I have just now described. Then we have Price, Simon, and then finally Barabasi and Albert. Okay, so without further delay, let's understand the Barabasi network. But before that, I would like to also tell you a simple theory about bipartite graphs. Now, I think you're familiar with this term, bipartite graphs, also known as bigraphs. Now, bigraphs are not digraphs. Obviously, they can be digraphs or they cannot be digraphs. So it's not like they have, since it is bi or di, they are same. No. So bipartite graphs are basically graphs where two dissimilar sets, two dissimilar entities are connected among each other. They are basically, you can say, a group. For example, basically, you can write it this way. Text, yeah. So you can write it as an ordered pair, A, so this is another this is one entity, this is another entity. So these two are connected as an ordered pair, so that relation between them, that is a bipartite relation. So bipartite graph, and they are commonly used to understand Hollywood actor network, collaboration networks, disease network, which we will obviously try to understand in the next slides. Disease network. So bipartite graphs. Okay, so let's start with the Barabasi-Albert network. The first given by Albert Barabasi and Rika Albert. Albert Barabasi is basically US mathematician, physicist, complex network theorist, and Rika Albert is Hungarian mathematician, physicist. So they would both work in the same lab. So they started Barabasi lab, which is a famous lab, Barabasi lab, which we are going to talk about a bit later. So Barabasi-Albert produced a model based on random graphs, based on stochastic functions. So they gave an idea about preferential attachment mechanism, applying that preferential attachment mechanism, that Marshall's rule, Matthews principle can be applied to complex network graphs, and that's how you can basically model any real world situations, any real world networks. So that was the Barabasi-Albert network model. So here is a small simulation of that model. As you can see, the new nodes are being formed and are connected with the nodes having higher degrees, as you can see. So this is a small rough simulation of a Barabasi-Albert model. So the applications of BA model. So the main application of a BA model is given by Barabasi and Albert was first the symptom-disease network, which we are currently working on, actually, which we are again going to discuss it later. But the main application was the symptom-disease network. So he gave a very simple logic. So he studied genomes and phenomes. There are phenomes are basically what you can say observable characteristics. The characteristics of any system which is observable can be called as their phenomes, and genomes are basically the genetic content, the makeup, genetic makeup. So different genes interact with each other in different manner because they are basically proteins, right? The genes are basically proteins. They are formed by the genetic material, which is the DNA. The DNA basically is nothing but a protein. So the protein, the different kind of proteins interact with each other, also known as the protein-protein interaction network. So they interact with each other, forming a gene network. So Barabasi proposed a model where the genetic content of the disease, or genetic content of the how the genetic mutations occur when a disease is upon us, that genetic network, how these genes interact with each other and they are getting affected. So that is a separate network he designed, and another network he designed is known as the phenome. The characteristic, the observable symptoms which are present when a disease happens. So these two networks, so gene and disease. So as you can see, the gene is a set and phenome is a set. They're two separate sets, but that which we also called as a bipartite network, right? So we have already discussed it, bipartite. So, but they're connected. They're undirected. They're connected in an undirected network. Yeah, so there are random graphs, individual random graphs. They're connected with each other, also known as a multi-layered graph system. So the BA model, with the help of the BA model, that is Barabasi-Albert model, Barabasi actually tried to identify and isolate how different kind of symptoms are related. How for example, there are certain diseases which have similar symptoms. So how these symptoms behave as a cluster, as a group, as a network among each other, with the help of two separate networks and combining them. So it's a bipartite relation. Yeah, so that's a huge important model. Another BA model which are currently used is the outbreak evaluation model. Outbreak evaluation model is basically a heuristic model based on the power function, heuristic power function. So it can be used to study any kind of global pandemic or outbreak of any kind of disease. So it is being used to study SARS-CoV-2. It's basically what it does. The model does is to predict what are the likely places, or what are the places where the disease is going to hit next. There's a likely places where the disease are going to hit next. So that is the main output of the BA preferential model of outbreak evaluation. Okay. Yeah, so it's a very another huge application of systems network, that is complex network, is systemic risk assessment using world risk index. Now these are quite complex terms. I don't think you are familiar with the word systemic risk assessment. Now there are two kinds of risks in case of market. When I am talking about risk, I'm talking about market. There are two kind of risks that generally occurs in market situations, in any kind of market. It's economic, obviously, economic market. So one is systemic risks and another is unsystemic risks. So systemic risks. So systemic risks are non-systemic risks. So systemic risks are those risks which are inevitable, the risks which we cannot avoid. For example, 9/11. You see, 9/11 affected the global market. After 9/11, the World Trade Network was it was vulnerable, so lot of money was lost during depressions. That was vulnerable. We couldn't know whether it was not predicted earlier that this was going to happen. So that kind of risk, the risks which we cannot predict, are called as the systemic risk. And there is another kind of risk, also known as the non-systemic risk. So those risks are basically which we can control. For example, you are an investor. Let us assume you are an investor. You went to buy some stocks, right? We are all familiar with the word stocks, right? Stocks means shares of a company. So when we buy some stock, it is we bought, for example, we bought just a single stock, it's just a single share, and the company went bankrupt. So what is our loss? Our loss is 100%. Now again, if we buy 100 shares, our projected loss will become 1%. It will decrease. So that is so the risk we take, that kind of risk we take is known as a non-systematic risk. But in general, systematic risk always exists because it is unpredictable. So systematic risks always exist in any kind of economic transactions or any market scenarios, any kind of companies. So complex network can be basically used to identify key factors contributing towards systemic risks. Then it can also be it can also be used to study how individual companies behave in terms of their own risk evaluation or own risk behaviors. For example, how different companies behave if the stock price of one company falls, and how those companies might behave, so from the risk point of view. So those kind of studies can be easily done with the help of complex network. So it's a huge tool for in risk management in economic studies, to identify those behaviors in such networks where risk study is necessary. So complex network is a very important tool. Okay, so another important topic which is getting more and more popular is the citation network. Citation, as I have told, the groundwork was laid in 1976 by Price. So citation network is very important. So what it is basically is, what is citation first? So what citation is basically nothing but when you write an article, when you write anything, you basically if you quote some line, then you tell the reader that I have quoted from here, I have quoted the line from here. So that reference you make with the original text from where you have taken that line, that is a reference. So that is a reference or a citation. So that is a citation. So in a single article, in a single research article, there can be thousands, or maybe not thousands, obviously it's not, maybe hundreds of citations. It could be there hundreds of citations, or maybe few tens of citations, or 15s of citations. So it could be there. So those citations are basically, they form a network, because one citation links a paper, a particular paper, to another paper, and that may be used for citation. Okay, so that is a citation network. The citation network is basically studied with the help of complex network. Okay. So after the citation network, we have collaboration networks. Now, collaboration networks are basically how various entities behave when they collaborate with each other. So there is some interference coming with the audience, from the audience.
Please mute your mic. Apart from the host, please mute your mic.
Yeah.
Thank you.
So yeah, okay, thank you. So collaboration networks. So collaboration networks are basically networks where which are used to study how different kind of peoples, different kind of entities collaborate with themselves, collaborate with each other. There can be collaboration among different countries, how different countries collaborate on in terms of military, in terms of how different countries collaborate using trade for trade. So those kind of collaboration can be studied with the help of collaboration networks. There are another very important collaboration network is a research collaboration networks. That is also very important. So that is also studied. So yeah, so research funding network can also be studied with the help of complex network analysis to study collaboration networks. Okay. Yeah. So finally, another huge aspect of studying collaboration, a huge aspect of studying complex network is its use in physics. So as we know, our universe is expanding. So it's a physical phenomena. It was first proposed by Hawking, people like Hawking, Freeman. It was that universe is connected. All the entities of universe is connected. So that can be that was first put forward by these physicists, So but the idea that it can be expressed with the help of a complex network, that came much later and was proposed by basically Barabasi, who gave us the Barabasi model. So that is also known as the cosmic wave theory. It was published in in the article "The Network Behind the Cosmic Web" by Albert Barabasi. Okay, now a short video from Barabasi Labs explaining, not explaining, basically showing us how the research is being carried out, how the simulations, how different kind of simulations are made with the help of complex networks. Yeah. Okay, so this is a small video of the complex network. I'll send you the links later. So, due to some reasons, don't think that due to some network issues, I don't think the sound is reaching. The video sound is reaching to everyone, but I'll send you the recording later. From there, you can basically identify the network. Okay. So, to summarize what we have studied what we have understood in this session here. So we basically studied what are complex networks, basically tried to question what are complex networks. Then we studied how to study them, how to study these kinds of complex networks. Then we asked that how can complex networks, what are the different parts that are present while studying complex networks. Then we studied different models of complex networks, for example the Erdős Rényi model, the Watts-Strogatz model, and the famous Barabasi-Albert model. And then we studied their applications, how these models, how complex network theory can be carried out in day-to-day life, in day-to-day interactions, and also in others simulating environments where complex network theory is used. So we have also studied that. We also covered the applications. Now we are going to say that what we are working on at Brain in terms of complex network. Yeah, so I will again like to thank Brain and Bread and Code for this session. So yeah, so we have what we are working on are the word networks, how different words semantically and syntactically they are related. So that we are working on. We are also working on trust networks, various trust networks, mostly medical trust networks. We're also working on the disease symptom relationship, how it's an extension of Barabasi's work, but on a larger scale, we are working on this disease symptom relationship and how it can be used to create certain medical applications. We are also studying social network behaviors, social ego networks, that is how various entities in social media behave based on certain parameters, based on certain topics. So we are working on these projects currently. Everyone is invited to join our lab. It's open to everyone. We want more researchers to work on these kind of problems. Yeah, so thank you everyone. If anyone have any questions, you can ask. Sir, you want to say something regarding this?
I have some actually question. Means
Yeah.
I want to get some view. Means what exactly you have talked about. Means the difference between the network and your graph. If you just repeat that thing, it would be much more better for everyone. I think so.
Yeah. So
Means what's the
yes,
difference? Means
yes.
how actually it can be differentiated.
Yes,
Okay.
yes.
Okay.
So the
Mm.
main difference between graph and network is the size. Means in case of graph, we generally tend to represent graph based on certain topics, certain specific topics. For example, in social media, we have set of friends. We are connected to certain people, right? In Facebook, we are friends with certain people, but not in general, not with everyone in Facebook. We are only friends with people we know, so that we can represent it as a graph, the friend graph. It's a social graph. But when we are talking about people connected in social media, people connected in Facebook, that is a social network. Facebook itself is a social network. That is the connection, how each and every people in present in Facebook is connected. Now that is how the difference works. Means in generally, graph is much more smaller than a network. It's a particular entity, but we focused on a particular entity, whereas network is an overall view of the, it's a generalization of a topics basically.
Okay, that's great. But I think you have some misconception because I'm not sure about that. But the network is basically based on the graph.
Yeah, obviously, graph is the building of
obviously, and
all networks
of
are
course.
actually graphs. All networks are mathematically they are graphs. But I'm just
Yes, of course
describing
it's graph.
the scale. The scale. In general term, how we can call that our network is a network and a
No,
graph
that-
is a graph. It's just a way of
no,
isolation. That's all. But in general, they're
yes,
same.
but
They're same.
yeah. In general, they are same. And in graph, what you did that in graph is basically in computer science they are nothing but a small or big. If we have
Yeah.
in something we can call it as small, yeah. If it is big, we can call it that is also a same possible. So graph and network is basically the same thing. And what about the properties? And you said about the properties. So basically, networks have more properties, more properties or less properties. It is not something like that. If we can consider each node of a graph, and we can put n number of properties inside it. Maybe a graph node has much more number of properties than a normal network or than a social network. It can be also done this kind of graph is simulated. It's seemed in small complex hydra or hive type of system. You can search in it with a much more properties. So graph and network is basically the same.
Yeah. You are right. You are absolutely right. So
means it is very clear from this discussion that we can say that the graph and network are actually the synonym. If you basically consider the graph means more, it's basically means to relate with the mathematics, and then rather than that of your actually the application. Means if you just go for the mathematical aspect, then definitely the network can be
called
considered
as
as
a
a
graph.
graph. It's
Yes.
nothing.
Yes.
Yes, that is what
Yes.
actually you are going to say over here.
Yeah.
But actually, means you are basically concentrating on that what particular portion. Means say it's for a particular person's network, means social network. I say, in that case, you are actually concentrating on a specific part of that particular network. So
Yes. Yes.
means you are basically moving on on a particular part. So that is also actually the graph.
Yes.
That is actually the graph. The whole thing is actually the graph if you think in that way.
In general,
And
yeah.
in a small part, it's you can think it is a sub graph. I think so.
Yeah,
It's for a particular
that is a
person's
better term.
social.
Yeah, that is a
Yes,
better
that
term.
is a better
Subgraph.
term.
That is a
Yes,
better term.
Okay.
subgraph.
Subgraph.
So
Yeah.
that is
Yes.
what actually the thing you are going to discuss.
Yeah.
Okay,
Yes.
nice discussion, and if everyone might have got a very good idea about this complex network, the people might be interested to learn more about this
Yes,
thing
so we are
and
basically
work
planning
on
on
this on.
a series of
Hmm.
videos concerning going much more deeper into each and every individual theories. For example, we can have a talk on how, on based on certain different topics. For example, one day we can discuss about citation network. The next day we can talk about only the Barabasi-Albert model. So in that way, we can move forward with our discussion.
Or it could be done in another way. If I would suggest in that way, definitely, that the method, if we can do, if we fix a particular means application based, means a particular
Yes.
application.
That also
And
can be done.
if I go, and if that particular application you are basically going to discuss,
Yeah.
what kind of theoretical means network model is basically applicable
Concepts.
in
Yeah.
that particular application, it might be very useful and very thought provoking in that case. I think so.
Yes. That is
So
a
you just
much better
plan for
approach.
that.
Yeah. That is a much better
Yes,
approach.
you
Yeah.
plan in that way. Okay.
Yes.
Okay, thank you.
Okay.
Thank
Okay,
you,
so any
everyone.
questions? Any more questions?
Uh,
Anyone from the audience regarding this?
Any question or suggestions?
Any
Anything?
suggestions?
Okay. So I think no one have not any other question.
Okay.
So
Okay.
it's the time to wrap up.
Yeah, it's
Thank
time to
you
wrap up.
everyone for being there. Please fill up the
Feedback form. Yeah.
feedback form, and thank you for this.
Okay. Thank you.